Hello, my name is DesireeRaju, and I will be presenting on groundwater depletion and sustainability in Merced County from my master's capstone project at the University of Arizona. This is an analysis which leverages geospatial technology to model and track broad localized groundwater trends in Merced County. The Central Valley produces over 25% of the nation's food and provides up to 60%, groundwater provides up to 60% of California's total water supply, specifically during drought. Groundwater pumping increases significantly in Merced County during periods of drought, and small communities in Merced County face heightened drinking water vulnerability due to groundwater reliance. Merced County is critically overdrafted, prompting an urgent need for high-resolution groundwater monitoring to support local planning and sustainability. Merced County is just over 1,900 square miles. It's an agricultural-driven community. It is both drought-prone with high dependence on groundwater. Merced County spans 3 sustainability groundwater agency subbasins. One in the center of the county, it's the main subbasin indicated in green. One to the northeast, indicated in purple, and one to the west, indicated in orange. Aquifer conditions differ across subbasins, affecting recharge and storage potential. The goal for this project was to downscale coarse GRACE land water equivalent data, integrate remote sensing and well data, and to estimate anomalies and volume, finally validating that information against water budgets and diagnostics. This slide here mentions the key data sources used for this analysis. The data sets used were GRACE satellite data for land water equivalent, GLDAS NOAA for soil moisture, evapotranspiration, and snow water equivalent, MODIS for surface water, and official reports by California Department of Water Resources and Merced Subbasin Groundwater Sustainability Plan. This slide shows the methodological workflow used to achieve project goals. First, starting with data acquisition, ending in visualization and communication. Data acquisition and pre-processing were a significant part of this project, as the analysis required the use of many variable rasters for the time span of 12 years. This slide displays the process for GRACE downscale, starting with variable isolation. Next, the creation of year-specific models, finally variable selection and model fit evaluation. GRACE downscaling enables high-resolution groundwater analysis across Merced County by integrating hydrologically relevant surface data and terrain information. After determining explanatory variables for analysis, different regression methods were trialed to determine which best predicted the dependent variable and spatial relationships. The methods I tried were OLS, which failed due to spatial autocorrelation, GWR, which failed due to multi-collinearity despite low VIFs. Finally, spatial autoregressive model captured spatial dependence and made it was a successful regression. The next step was interpolation and outlier removal. Imperial Bayesian kriging was used to handle sparse well data. And for this analysis, I removed outliers plus or minus 3 standard deviations away from mean. This helped avoid artificial trends, fill spatial gaps using regional patterns, and improve regression model accuracy. Data was modeled both before and after outlier removal. The map on the left shows data modeled with outliers, and the map on the right shows modeling after outlier removal. This graph shows water volume estimates derived from downscaling GRACE land water thickness using the method of spatial autocorrelation regression. The spatial autocorrelation models balance between EBK and observed LWE, reducing extreme spikes in data. Overall direction of water volume change matches the GSP water budget, although magnitude differs. The difference in magnitude may be due to data sources, spatial resolution, or interpolation method. This confirms modeled results broadly reflect GSP observations, adding confidence in remote sensing and integration with well data for water management. All models detect recharge in wet years, 2013, 17, and 2022, and depletion in drought years, 2014, 2015, 2018, to 2020 and 2023. EBK sensitivity, it's very sensitive. It picks up larger changes, so it's great for detecting localized extremes, but more prone to overestimation. Anomaly detection is in directional agreement with GRACE, but there is extreme anomaly underestimation for the year 2023. Overall, long-term net decline despite wet year recharge. All of the data agrees that wet years were 2017 and 2023. These were large positive spikes in the data. Dry years, 2014, 15, 2018 to 20, had deep negative drops indicating dry or drought years. This analysis was able to pinpoint temporal trends of recharge, plateau, rebound, and aligned with sustainability plan, the reported periods of drought and recharge. Timing of depletion and recharge as reported by the Groundwater Sustainability Plan are best tracked using spatial autocorrelation regression, downscaled land water thickness. SAR also matched magnitude more effectively than interpolated data. EBK outlier was sensitive and useful for detecting local anomalies, but less reliable for basin-wide totals. All three datasets capture the same multi-year drought recharge cycles documented in the GSP, confirming the validity of anomaly detection. The limitations of this study, there were quite a few gaps in available in situ well data. So there was really reduced coverage. It required interpolation, possibly introducing bias to the analysis. Another limitation, model assumptions assume relationships are constant, and that may not be true in the real world. Sensitivity to extreme values, outliers can really influence model and volume estimates. And finally, this analysis does not focus on seasonal variations of recharge or depletion. Future direction, to expand on this analysis, it would be beneficial to integrate seasonal data, incorporate additional variables, improve outlier handling, cross-validate independent data sets, simulate impacts of droughts, recharge, and pumping restrictions. That was very quickly the end. I'm sorry I rushed through that. If there's any questions or anything you'd like to hear me elaborate on, I would be happy to.